Hello and welcome to today's lecture. So today we're going to continue our discussions about graphs. So this is the third and final lecture on graphs. So in this lecture we will be talking about matching problems, and there's a large variety of different matching problems, and we will also talking about covering problems. Then this also includes the Euler path, which is part of Lab 2.9. So if we start with matching, so a match in a graph G is a subset of edges in G without common vertices. And I mean, one example that's being often used here is the marriage problem. So basically finding pairs of partners to marriage and that there are no affairs. And then that's an example of a matching where every person can be matched to a partner. Then we have in some sense the optimal solution. So here are some examples of matching. So of course, if we have two vertices and an edge between them, that edge is a matching. It could also be, this is also an example of a matching because it's a subset of edges and there are no common vertices. On the other hand, this is an example of that is not a matching because the lower node is included in two matches or edges. So therefore, this is not a matching. Here we have a fourth example, which is an example of a matching because here every pair of we have two edges that's included in a matching, and there are no common vertices. And here we have an example of something that's not a matching because in this case every node is in two edges, so therefore it's not a matching. So a matching is then a subset of edges so that there are no common vertices. And now we might be interested in a number of different things. I mean, of course, we're interested in finding a matching or all the matchings, but normally what we're interested in is finding a maximum cardinality matching, which is the matching with the largest size, the most number of edges that we can find in a particular graph. And this is then different from maximal matching. And a maximal matching is a matching for which we cannot add any more edges. So I mean, it might be the case that we cannot extend this any further than it's maximal, but it might still not be maximum. Of course, the maximum cardinality matching is also a maximal matching. So that's a maximal matching is a subset or a more inclusive concept than a maximum cardinality. And in order to come to the actual algorithms for solving this problem, it's very important to consider one particular type of graphs, namely bipartite graphs. And I mean, we've had bipartite graphs before in this course, but it is a graph whose vertices can be divided into two disjoint sets, such that every edge connects a vertex in one of these sets with the other. So there are no edges within these two sets. So all the edges are between them. And if this is the case, then things become much easier. And here is then an example where we have all the blue vertices on the left, and every blue vertex is only connected to green vertices on the right, and there are no edges between any pair of blue vertices or any pair of green vertices. Now we can come to the maximum cardinality bipartite matching, which is then the problem finding the size of the largest possible matching in a bipartite graph. So if we have this an example here, we have 5 nodes on the left and 6 nodes to the right. It's basically, I mean, in this case, we can match every node on the left with a node on the right. And here we have, in some sense, a perfect matching that every pair of every node is matched to some node, and yeah, and then we have the second problem, which is the weighted maximum cardinality matching, and in this case, it's that the edges have different weights. And now we want to either find the maximum cardinality matching with the lowest weight or the minimum weight or the maximum weight. So there might be multiple maximum cardinality matching. We might also be interested in just finding the maximum weighted cardinality matching. So in some sense, we just want to find this the subset of edges with the largest sum of weights, such that it's a matching, or the minimum for that matter. So these are some variations that, of course, make this problem a bit more challenging. And if we then want to come to the actual different solutions to this, the different algorithms, we can make a decision tree as the following. So the most important question is this graph bipartite or not? If it is bipartite, then the problem becomes much easier. And then the second question we need to ask ourselves, is this a weighted problem or is it an unweighted problem? So if it's an unweighted bipartite problem, then we can just solve it using maximum flow. And I will also show a kind of specialized algorithm called augmenting paths, which is actually very similar to kind of the maximum flow algorithm we saw in the previous lecture. If this is a weighted problem, then instead of using a max flow solution, we can now use a min cost max flow solution. So again, we can reuse the flow algorithms. If it's not bipartite, then becomes trickier. And actually, this was a problem where many people thought that this was an NP-hard problem until it was showed in the 60s, I believe, that there is a method called the Edmonds matching for unweighted maximum cardinality matching. If it's not bipartite and weighted, then it becomes harder, again, of course. So here we can only deal with small graphs using dynamic programming with bit masks. So basically representing the subset of edges that we include in the matching, and then we can search for the optimal solution using that. So of course then the question becomes, how do you formulate the max flow problem so that you can solve the maximum cardinality bipartite matching? And actually it's quite straightforward, namely that you have the bipartite graph in the middle, you add a supersync and a supersource, which connects all the vertices on one side of this bipartite graph, and all the edges in this problem have capacity 1. And now you find the maximum flow in this graph, and that will be the same as the maximum cardinality bipartite matching. So straightforward, and just shows the kind of power and versatility of max flow, which is a very useful algorithm for many things. Another way of doing this is to work with augmenting paths. As we saw in the previous lecture, a path is called alternating if the edges between vi minus 1 and vi and vi plus 1 alternate between matched and unmatched vertices. And P is then augmenting if it is alternating and vi and vk are unmatched. So basically going from one unmatched node to an unmatched node, where every second intermediary node is matched and every second is unmatched. So just to give an example, assume that we have an original match up on the top here. So we have 4 vertices and we have matched the 2 middle vertices with the red edge. Now we can start in the leftmost vertex because that's unmatched. We can go to a matched node, which is then the top one, and then we go to the low one, and then we go to the, so we're alternating here. So we go visit all the 4 vertices, and now since we have found one of these augmenting paths, we see that every second edge is an unmatched and every second edge is matched. And now we can just flip these, and by flipping these we will increase the matching set by 1. So, and then in this particular case, there are no matching. So now we have found the maximum cardinality matching. So this is a very nice approach. And this is then, of course, connected to this nice lemma by Claude Berger from the 50s that says that the matching M in G is maximum if and only if there is no more augmenting paths in G. So this is then actually a way of solving all these matching problems in graphs. And it has the complexity order V of E to implement this. So actually this is of course related to the Edmund Karp for the maximum flow. So they are of course quite related. So that was a bit about this cardinality matching. We will now talk about the independent set and covers. So an independent set is a set of vertices in a graph for which no two vertices are adjacent. So it means that there are no edge between them. And we also have something called the maximal independent set, which is a independent set such as we cannot add any more vertices to it. So again, it was similar to this maximal cardinality matching instead of maximum cardinality matching. And then, of course, we have the maximum independent set, which is the largest maximal independent set. So of all the maximal independent set, which has the largest number of vertices in it, that is the maximum independent set. So here we have 6 examples of maximal independent sets. So we can see on the upper left, we cannot add any vertex because every vertex has one of their 2 red vertices as a neighbor. So therefore it's not possible to add anything more. On the middle top and the middle bottom, we see that we have 2 examples of maximum independent sets. So here we have 4 vertices in the maximum independent set. We cannot add any more. Then we come to the cover problem. So a vertex cover in a graph is a set of vertices that includes at least one endpoint of every edge. So in some sense, we want every edge, at least one of the 2 vertices of every edge to be included. That's a vertex cover. So here we have 2 examples of vertex covers. On the left, we have 3 of the 6 vertices, and on the right, we have 4 out of the 6 vertices. And now, of course, we might be interested in a minimum vertex cover, meaning that we want to find the smallest set of vertices that covers all these edges. So in both of these cases, we can actually reduce. So on the left example, it's sufficient to have 2 vertices in the minimum vertex cover. So of course, so in some sense you can see it as the top red vertex will cover the 5 edges going out of it. And then there is one edge at the bottom, which means that we need to include one of those 2 vertices there in order to cover all these edges. On the right, we see that we need to basically include the top middle vertex, and then we have covered 3 of the edges. We can then say we can take the lower left node, and then we add that, and we have covered 2 more edges, and now we have 1 edge left, and then we have 2 choices, either the one that's colored red here, or the one to the furthest left. That could be an alternative to that one. So again, the minimum vertex cover is then 3. And here there is an interesting theorem, namely the Koenig's theorem, which states that in any bipartite graph, the number of edges in the maximum matching is equal to the number of vertices in the minimum vertex cover, so that there is a direct connection between these 2 problems, between the maximum matching and the minimum vertex cover. So it's kind of related to this max flow, min cut, which is basically the same idea. And it also means that in a bipartite graph, the complement of a maximum independent set is the minimum vertex cover. So that is the way to connect them. So for example, we have a problem such as this. We find the maximum cardinality bipartite matching, basically the two red edges there. Then the minimum vertex cover will be the nodes to the left there, 1 and 7. So if we take those two vertices, then we have covered all the edges. And then the maximum independent set is just the complement, which means that it's the remaining 3 vertices there. So this brings us to the last part of this lecture, which is then also the content of Lab 2.9. And here the problem is about finding the Eulerian path, which is a path in a graph that visits every edge exactly once. So if we have a graph such as this, and we can see if we just follow the edges in the alphabetical order, A, B, C, D, E, F, G, H, I, J, K, we see that we have then visited every edge exactly once. And then this is actually also an example of an Eulerian circuit, which means that it starts and ends in the same node. And here we have the kind of famous theorem, and it says that there is an Eulerian circuit if and only if the degree of every vertex is even, then that this is possible. We also can relate this to the Hamiltonian path, which is then a path which visits every vertex exactly one. So this is just an example of a Hamiltonian path. So of course now the question becomes, how do you compute the Eulerian path? And here we can use Heer-Holzer's algorithm. And it's quite straightforward. So basically we select any starting vertex V. We then do a, for example, depth first search. So we follow a trail of edges from that vertex until we come back to the vertex again. So for example, we can take the blue circuit below. So we start in node 1, we go to node 2, 3, and 7, and then back to 1. So now we have found a cycle. And what we do then is that we find a vertex in this cycle where there are unvisited edges. So for example, we can start in 1 again. So then we can take the red circuit. So we start from 1, 3, 4, 7, 8, and 1 again. So now we have covered all the red edges. And then again, we find a vertex on this or on any of the existing circuits which have unvisited edges. So for example, number 4. And then we do the green tour. So we go 4, I guess 5, 6, 7, 9, 4, or I mean 4, 5, 9, 6, 7, 9, 4. And now we reach back to number 4. And now we have visited every edge in the graph. And now we're done. So now we just add all these together, and then we have found the Eulerian path. And of course, the time complexity is clearly order E, because we will visit every edge exactly once. So that's clear. So this is then the solution to Lab 2.9. So in this lecture, I've been talking about matching problems. So basically how to select subset of edges in a graph so that there are no vertices covered by 2 edges. So basically that means that every edge represents 1 matching, and we want to find that every node, every vertex is only matched to at most 1 other vertex. And then we have a number of different things here. So maximum cardinality matching is the kind of general problem, or rather I would say the maximum weighted cardinality matching is of course the most general version. And then we can simplify this in 2 directions. Either we can remove the weights or making the weights uniform, or maybe I should say we can simplify the graph structure into bipartite graphs. And then depending on which structure and what problem, you get a number of different solutions, but many of them are related to max flow. So using max flow, we can solve the maximum cardinality bipartite matching. If we use min cost max flow, then we can also solve the maximum weighted bipartite matching problem. And if we want to solve the more general problem, then we have to use Edmonds algorithm or dynamic programming using bit set techniques. Then I also talked about covering problem. So for example, we want to find a maximum independent set, which is then finding vertices that have no neighbors. So you cannot have, so basically for every edge, we can include at most one of the two vertices. And in some sense, the minimum vertex cover is then the complement to this. Here we want to include all the edges, the minimum number of vertices such that every edge has at least one of its two vertices included in that set. And these are then the complement. And finally, we talked about the Euler path, which is finding a path through a graph that visits every edge exactly once, and this is then part of lab 2.9. Okay, thank you very much and good luck.